for some reason I start sneezing.
Hi, Asif.
Oh, hi, Albert. You are also you're remote. Okay, I was wondering.
I was planning to come, but somebody came over, and that's why I kind of couldn't drive yet.
No problem at all. All right, so I'll just recap. Today is our final session. The first thing I would like to do, of course, is to congratulate you all and remind you that your certificates are ready. If you do see your certificates, please add it to your LinkedIn profile. You can use me and support vectors as your reference if you are ever interviewing for jobs in MLOps. We would be happy to be your verification and reference that you do know this subject. Also, with that there, this portal will be accessible to you all the time. So do not hesitate to reach out to us if you have more questions in the field. Our courses are endless. Also, please be reminded that our courses are evergreen in the sense that if you register for the course once, it gives you access to every repetition of the course. So when we teach this course again in spring, and by then, more things will come up. The subject, as I said, itself is evolving. Whatever new things, unforeseen things are there. For example, now, by the time this course finished, prompt operations have become something big. We never quite got time to get to prompt ops because it was a fast-paced course. But in the next iteration, you'll see that there will be a place for prompt ops into this level. So you're most welcome to come and repeat the class and watch the videos and contribute. And do stay connected with us on the Discord channel. What I'm going to do today is going to review all that we have done in this course. Now, as I was saying, this course is this profession of MLOps and LLMOps and now emerging prompt operations. These are tough professions because to do this, you have to take a more broad perspective in the field. You can't be siloed into one corner and just do your stuff. You have to collaborate with different tribal cultures of sorts. And the different cultures that we talk about in our field are things like data engineering. Data engineering is a big word. It has data manipulation, quite a bit of ETL, extraction, transformation, and loading, or in the big data world, extraction, loading, and transformation. So in this world comes Spark, in this world comes Kafka, and many other things. In this course, we try to give you just enough introduction to data engineering, only those parts that were relevant to machine learning, to AI. And it incorporates not just ETLs and transformations. It's also like, how do you curate data? How do you get higher value feature extractions from the data? How do you validate the data? And how do you continually do that, version the data and worry about it in the presence of continually evolving data? How do you worry about data lineage, the data getting stale, data drift, distributional drift, and things like that? Those are the core concerns when you have with data. Likewise, you have core concerns with models. Any model, to the extent that it is a trained model, whether it is supervised learning or unsupervised learning or reinforcement learning, if you take the case of either, let's take the case of classifier or regressor, you need to know what data your model was trained on, because it will work well only on the kind of data for prediction at inference time data where inherently it belongs to or its nature is represented by the distribution of the training data. If the distribution of the training data and the probability distribution of the inference time data or runtime data are divergent, then you're likely to have the model underperform. And you have to address those issues of model drift and that ensues. Does that happen? It happens all the time. For example, if you're not, trends change, especially in retail, trends change quite regularly. And you have to keep retraining the models when it comes to recommender systems, etc., which are the staple diet of like e-commerce sites and search. Recency recency is a factor that's quite central to considerations of the recommender system as well as search results. So you have to worry about those things. Then you have to, as you train the model, you have to worry, do you have the hardware to train the model? There used to be a time when we could train models on commodity servers. You would get, for example, a two-way server with 2 Xeons or 2 EPYC processors and a bank of memory. And you would feel pretty pleased that you have got good hardware to train your AI models. You could, if you wanted to train a random forest or a gradient boosting or a support vector machines, you could get away using that kind of hardware. It would suffice. Now, we have entered somewhat new territory where having vector processing engines has become a de rigueur. You have to have GPUs, you have to have a tensor processing units, a matrix multipliers, or math coprocessors. You can pick the synonym that you prefer. But all of these things have become absolutely necessary. I just had a demonstration a little while ago. We were using a large language model here in support vectors, which was running on our inference server with 4 GPUs. We were getting inferences in literally as soon as you would enter the prompt and you would run the code. And the person complained that when he went home and ran it, it wasn't running. Then after some debugging, it turned out that the inference, while he thought that from his laptop he was connected to the inference server at support vectors, in reality, it was running on his Mac locally. And when it would do so, what was returning more or less in real time, instantaneously, with a very short time lag, was taking many minutes before anything came out. And so that speaks to the fact that even powerful contemporary hardware, like for example, Macs are usually considered premium hardware, and in laptop world is about as good as it gets, I'm told. It's not sufficient. We have entered a field in which hardware defines what you can and cannot do and what the latencies will be. Right? There are models that you simply cannot train unless you have a bank of GPUs. Right? And what does that mean in terms of MLOps in day-to-day enterprise life? You will go to the infrastructure team and they will tell you that, okay, there is only so many GPU servers or GPUs available. You can, in a sense, borrow it for a limited time if you give a very good rationale for why you need it. And obviously, when you get that for a limited amount of time, you have to make every effort to use it optimally. You can't waste time. You have to train your model within the bandwidth or the budget of time that you have been given. These are practical realities today. And you have to explain why you're continuing to train the model. You have to use all sorts of arguments about optimal training computes. And so for neural scaling laws, you have to look at to determine what is the right size of compute that you need to train a model, how much data you bring. And I don't know if in this course we talked about neural scaling laws and the chinchilla optimal and things like that. We have certainly covered that in our regular Wednesday paper reading. So many of you may be familiar. Would one of you remind me if I covered neural
No.
scaling?
So our course was very focused on labs. So we did quite a bit of Ray framework. As part of it, yes, we did cover some scaling, how you scale the workloads across cluster. But I don't think we covered any neural scaling law as such.
Okay, so maybe today I'll just take some time out to cover that topic because it's important to walk away in MLOps. It's an omission. I should have covered that. I will cover it today. That makes for an interesting topic then. And so that is that. Then comes the evaluation metrics for models. See, when you talk of classical models, like, the things that we have been used to, discriminative learning, classifiers, regressors, clusters, more or less over the years, over the decades, excellent metrics have evolved. If you were to think of regression, for example, you would look at mean squared error, you would look at adjusted R squared, you would look at mean absolute error or mean MAPE and so on and so forth. There's a whole slew of correlation coefficient and so on and so forth. There's a whole evolutionary bag of metrics over the years. If you look at classifiers, you have accuracy, precision, recall, sensitivity, specificity. You have the ROC curve, area under the ROC curve, and there are many derivatives from the confusion matrix. Right? So they have stood the test of time, those metrics, and they have served well, the AI community. They have really served very well. So we don't generally these days spend a tremendous amount of research on discovering new metrics when it comes to classifiers or regressors. That is not to say that new metrics cannot be discovered or what we have is necessarily perfect. It is just good enough. Our work gets done. We have begun to trust those metrics. Likewise for clustering. Clustering is unsupervised, so it's a little bit harder to quantify or evaluate the quality of clustering. Nevertheless, we do have the ELBA method, the Siloid method, and all sorts of things trying to establish the convex hull and so forth. And over the years, a battery of metrics have evolved for clustering algorithms also. So you can look at these metrics and make sure as an MLOps person that the models that the AI engineers are submitting and trying to push to production, they do pass through your metrics, and the quality only improves on reference data set. So given a model version, you do want to maintain some data versions and make sure that the output or the metrics only get better. Otherwise, you don't promote those models to production. And those are the AI metrics or the machine learning metrics. Sort of together, complementary to it are other metrics, actual traditional computer science metrics. What is the compute cost of that model? What is the latency associated with it? What is the throughput through the model? These things matter because these have direct impact on the hardware. And we do need to worry about those things, as you will see. Now, all of these considerations, they get even more exaggerated. And I didn't talk about reinforcement learning, but similar considerations apply. At the end of the day, we have understood some of these things. But when we come to generative AI, then it gets a little bit harder to do things. For example, you could say that I could use when some text is generated from a large language model. You could use a causal loss. You could say, I was expecting the statement, the cow jumped, and it should be followed by continued with over the moon. And what I got was the cow ran around the meadow. And you might not like that answer so much. You said my expectation was that it would jump over the moon. And so you could look for causal loss and quantify it. But generally, it's a little harder in the generative world to evaluate the metrics. And not just the generative world. The generative world has its own bag of problems. Like, for example, an LLM is capable of both understanding the language, an ability that is most remarkable. You take a large language model, let's say you take Llama 3.2. What you do expect are two qualities from it. First, that if you give it a text, it will be able to understand it, which it seems to be doing beyond our expectations. Nevertheless, not perfectly. The second aspect is it seems to remember a lot of facts in its parametric memory. One of the things that people used to believe is that these are just weights and biases. So these models potentially don't remember anything. They're just using a probabilistic model to generate the next token and the next token and the next token. And it appears as though it remembers, but it doesn't quite remember. Today, we know that that's not really true. There has been practical lawsuits, like, for example, the New York Times lawsuit against OpenAI, which showed very, very convincingly that the LLM was practically reproducing the article verbatim, the articles of New York Times verbatim. And there was this whole issue of copyright violation and so forth. So obviously, the whole copyright issue has to be completely rethought from the ground up in the world of generative AI. That's a topic in its own right. Artists are getting up in arms and so on and so forth. But leaving that aside, we do know today that somewhere in the layers in the feed-forward network, especially, we believe that there is a lot of memorization of the content that the models are trained on that's going on. So now we have two different aspects to a model. A level of understanding. When it responds partly from its understanding of the data, of your input, but it also responds from its own parametric memory. Now, why would that sometimes be a concern? Consider the situation of retrieval augmented generation. When you do RAG, you search for things in your, let's say, corporate database, data corpus or document corpus. You would rather that the answers are completely grounded in the documents you feed. There are situations where you don't want the LLM to pull things out from its memory, even if those memories are right. A very trivial example would be, let us say that you are company A, and your document, you have some marketing and sales and customer support documentation. When responding to a user prompt, a user input, you don't want your you want your LLM to mostly suggest, if the user says, can you suggest what product will help solve my problem? You would rather that the LLM proposed a project from your sort of offerings, whatever products that you guys, that your company offers and is documented. What you don't want the LLM to do is to very helpfully point out that one of your competitors' product is far superior, and it would be a good idea since to just go and buy that, right? Or anything like that. So that's a classic case when you don't want the LLM to remember things that or use its memory, but you do want the LLM to use its ability to understand, the language understanding part. So now comes a very interesting thing. You realize that your classic metrics of machine learning, your metrics for regression and for classification, and even your metrics for causal loss, right, are not exactly useful. How do you prevent this? And it opens up a whole new field, and new ways of evaluating these large models, large language models, as we call, or transformers, as we call them. Right? So those evaluations are important, and that's a fast evolving field. As of this moment, quite literally, LLM, how does a LLM judge the output of, for example, another LLM, or what it has produced, is one of the hottest areas. As a bit of news, some of the people right here in the room, they from in another course, they went to San Francisco. There was a competition, a hackathon, to build LLM as a judge. They happened to have won amongst the 30 or 40 teams that competed. I think they were in the top 3 or top 4 or something like that teams. So they did extraordinarily well in creating a LLM as a judge. And they built the entire judge stack of their own with a good idea in a matter of just 2 days in the hackathon. So it just shows how this field is evolving. People are all worried, how do we evaluate this machine learning methods? So that is one extreme, which is very, very raw, very, very unfinished work. On the other extreme are the classifiers, regressors, the discriminative learning, the clusters, which are quite mature. Somewhere in between are things like, how do you see in a RAG? There are 2 aspects to it. First is the search, and then is the output of the LLM. How good is the search? For search, you would use metrics like MRR, mean reciprocal rank or mean average precision and things like that, which I believe you have, all of you, encountered in the courses that you have taken with me. So those things, and they are, again, I would say, almost well worked out metrics, but not yet perfect. For example, you might have very good MRR, but how does it know, mean reciprocal rank? But how does it know that, for example, you have given enough emphasis to recency and things like that, right? So you have to cook up metrics based on every context. So that speaks to the evaluation of ML models. It's tougher than you think. And it's one of the unsung heroes. See, today, if you look at the landscape of AI, every time a new model comes out, there's great celebration. So for example, recently Llama 3.2 came out. Amazing. It's the first multimodal open source, really high-powered model. Great celebration. So the model part is very well celebrated in our field. Perhaps not so celebrated is the endless labor that goes into preparing data to train the model, the data preparation. And that data preparation belongs to the world of MLOps and gathering label data, creating label data, cleaning up the label data. So for example, there's a recent paper, I think it's called Prox, which has an algorithm that greatly improves the quality of the in training data. And it shows that if you, instead of just training a machine with more data, you significantly use a smaller model to improve the quality of the pre-training data, then two benefits ensue. One is that the model that you build is superior, but surprisingly, another benefit that ensues is that it becomes compute optimal. In other words, it takes far less computation to train the model to a high degree of saturated efficiency than it would take. Now, you might say, well, that is true. And we have seen this trend. For example, papers like Textbook is All You Need have pointed out the fact that sometimes amazing data, very high gold quality data, beats more data. And that out of the Textbook is All You Need, as you know, the models that came out were the 5 series, 5.1, 5.2, 5.3. They're pretty, 5.3.5 is, I believe, the latest. So these are amazingly, these are little champions. They're like, they do quite an admirable David versus Goliath show. Right? And they are the Davids of the LLM world, tiny little models that and Gemma and so on, into the Gemmas and the Phi's. They are the little Davids, yeah, doing a pretty admirable work. But the question is, how is it that they're able to do that? They're able to do that because they're being trained on very, very high, I mean, in particular, the 5 series is trained on textbook data. Why textbooks? Because textbooks go through a lot of review and careful writing. You don't typically find a proliferation of grammatical errors, factual inaccuracies, and sloppy writing in textbooks. Those are relatively rare, thanks to the committee of reviewers who put in a lot of effort to perfect the structure and the content and the exposition of a textbook. So when you train a model with that, it does become pretty good, even though you're using a much smaller model. So that speaks to the quality, the importance of data quality. And there is, and one of the emerging areas in MLOps that we really couldn't cover because of a paucity of time is that what are the things we can do to filter the data, to clean the data, to improve the quality of the data. It turns out that you can do it using LLM itself, different LLMs. And in fact, one of the recent things like the Prox mentioned shows that little champions, little models do a very efficient and very, very compute efficient and amazing job of improving the quality of the pre-training data. And therefore, soon you will see, I would imagine that there will be tools, open source projects that will proliferate that help you do that in the MLOps. So that is one aspect of it that is likely to become now a part of your MLOps arsenal. Then, so that is the model management aspect of it. Models come with risks. How do you know that models don't have biases? It's yet another important topic that a short course like this doesn't cover. But obviously, if someday we do MLOps, advanced MLOps course, that would be a significant part. Why does it matter? Why does it matter that we check for bias in MLOps? Because of the ethical and profound societal impact of the model. And there's a lot of precedent to it. For example, it is a fact that these models, even when used in production, even when coming from really big AI houses, whose integrity should generally not be questioned because they put in quite a bit of effort to create good models. One of the examples is the Google search engine, apparently. One Harvard researcher, professor, did a very simple experiment, took a laptop to one of the, should we say, more left-leaning states and asked, global warming is and the search engine very helpfully gave an auto-completion. And it said it's an existential problem, right? On the other hand, or something to that effect. On the other hand, you took this, I don't remember the specific details, but if you took the same thing and with the same laptop and you were to do the same query in one of the southern states in the heartland of US, the answer was alarmingly different. It would say global warming is a hoax, is a complete hoax, right? So, which is very disturbing ethically and profoundly destructive to societal structure. Because, see, you and I, as two real rational beings, can have opposite perspectives on the same data, on the same facts. We may disagree what is right. For example, in this country, in the United States, there is a healthy debate that has been going on for many, many years on issues like abortion or many other topics. Some people are for it, some people are against it. And but at the end of the day, they are looking at the same facts, or they used to be looking at the same facts. It based on their different leanings, their religious convictions, their upbringing, their mode of thinking, they are each entitled to a different perspective on that issue. It's a thorny issue. It is not something so clear and black and white. But today, we are facing the alarming situation that almost all the news that we get from social media platforms, we get from these machines that are imbued with AI. Even the search we do, even the news we read, they are supposed to be served to us based on our preferences. The trouble with news, which is personalized, is that the goal of the algorithm is not to serve us an objective truth. In law, we speak of the truth, nothing but the truth and the whole truth. Trouble is, algorithmic systems never serve you the whole truth. They do not give you all aspects of a fact. What they do, as in the case of the search, is they selectively serve what you would like to hear, right? And because they serve what you like to hear, perspectives, they reinforce stereotypes, they polarize societies, deeply divide us, and it has, and if I may just go on a very small tangent, it has profound consequences, ethical consequences. And this is brought out, actually, the author of Sapiens, Harari, has written a new book called Nexus, in which he very strongly argues that democracy, a precondition to democracy is a free flow of information. To the extent that information flow itself is now controlled, and different people are being shown different realities, that provides a mortal danger to the democratic institution itself. And we can see that there is a retreat of democracy around the world. There is and for better or for worse, I mean, there are people who say the time of democracy is over. It is a thing that has outlived its usefulness. And there are people who are very fond of democracy, and that would certainly include me and my leaning. who really feel alarmed at the way algorithms are destroying the fabric of society and democracy. So if you were to ask this question within the fabric of engineering, who is responsible? Who should be the guardians of bias and unintended bias, or looking for destructive aspects of machine of these algorithms? Surely those guys who are innovating, who are rewiring neural networks in innovative ways and coming up with better algorithms, they would probably wash their hands of it. They say, we couldn't be bothered less. Any algorithm can do harm, it can do good. We are much more interested in pushing the frontiers of technology. In my opinion, that burden falls squarely on MLOps, because test for bias, test for adverse impact. The people who can do and who will do or who should do are the people, are the MLOps community. It is a bit of a regret that I couldn't bring in assignments or labs that would deal with that. Those are very interesting labs. But again, everything was conditioned on the fact that we had 7 sessions. Last session is always a summary. We had only 7 sessions at our disposal and the associated labs. So somehow the lack of time. But I'll just tell you the way the legality of this works. Today, all the countries are enacting laws because they are seeing what is happening. Europe has the European AI Act. And again, opinions vary. Some say it's too draconian. Some feel it hasn't gone far enough and it was crippled. Somewhere in there is perhaps the fact that, for better or for worse, EU Act represents our consciousness that algorithms can do harm. Many different countries are now rising up and creating their own equivalent of AI governance. In the US, National Institute of Standards and Technology has the risk management framework, RMF, which are AI risk management framework, which I highly encourage you folks to read as people who are going to be practitioners in MLOps. It is a very enlightening document and a short document, actually, only about, if I last recall, about 30, 40 pages of document. But it has some very, very good advice. It is mostly a set of principles rather than hard encoded do's and don'ts. But I feel that it is, if you are doing MLOps, it's an ethical obligation to be aware of those well thought out principles that can help you ensure that in your enterprise, machine learning is used without imposing extraordinary risk on society. And these risks are very rare. There are many cases. Amazon came up with an algorithm for hiring, which they swore has no bias, because the data with which they trained did not have bias. It was anonymized data. There was no gender there. There was no race there, and so forth. And nevertheless, I'm told that it did prove that it showed preferential hiring for men over women. And it had to do with and how is that possible? And the reason is the AI is very clever at figuring out what sort of people to hire based on the subtle biases in the training data. While the data was anonymized, it was inherently a fact that men tend to get hired a little bit more than women, given equivalent skill sets. And the AI somehow figured that that is what it has to learn to do, and it began to do it vigorously. They had to take down that algorithm because the law is the law. Law doesn't say that your data doesn't have any bias in it. What the law says is your model shouldn't have bias. And it comes as a surprise to people that models can have bias unless proven otherwise, even if the data does not have bias, or you believe data doesn't have bias. Data, you should assume data has subtle, invisible biases or hard to discern biases. Right? So that's the ethical responsibility. In the United States, we have laws that you should be aware of. These are called protected categories, protected classes. You cannot discriminate by gender. You cannot discriminate by age. You cannot discriminate by sexual orientation. You cannot discriminate by race. and so on and so forth. You cannot discriminate by disability. And if your algorithm, if you haven't put in your MLOps enough processes, enough tests, enough safeguards to check that the effect of your algorithm on society, on the users, is not one violation of one of these protected classes, then you have been amiss. You need to do all of those. So I'm just pointing out all the things that mature MLOps organization needs to do. These are becoming very, very real now. In fact, there was even a proposal that every AI house must have these things baked in and prove that they are compliant with that. Fortunately, it was thought to be too draconian, and I believe so there's a lot of self-governing and trust at this moment that is being relied on in the interest of moving fast. But the fact does remain that all of these things work on trust till it comes out that trust is violated or flaunted, rather, with impunity. But then, of course, laws get formulated. And so time will tell what is the right balance of safeguards and legal framework to wrap this in. But those things are all coming, definitely coming. Then comes the next phase, which is the dev part of it. You have you take your code, you build it, and so on and so forth. Your ML ops, your models are a small part of a larger enterprise application fabric. It has to go through the whole process of deployment along with the rest of the application. It has to have a life cycle of its own, right? And there has to be tests. It has to be processes for it. All the usual processes that you find in the dev world. But then there are things specific to machine learning, which are what today we call the world of observability. You do the release and the deployment. Okay, no brainer. Everything needs release and deployment and its proper processes to do it. But in machine learning, especially with large models, with transformers, these take on new meaning because unlike traditional machine learning or unlike traditional software, which can be deployed on commodity hardware, today, a large number of models use transformers or language models. Language models tend to be extraordinarily large, shockingly large. Like most traditional machine learning models would have at most a couple of thousand parameters maybe. But LLMs count their parameters in hundreds of billions. So we're in a different world. You need different hardware, very expensive hardware, where GPU is the scarce resource. Within the GPU, the memory that is planted in the GPU, which generally we call the high bandwidth memory, HBMs, are at extreme premium. They're very expensive to imbue into the GPU. And so you have to rethink the entire architecture of production, which has been happening. In this course, you learned about one of the more successful architectures of frameworks that help you manage your training, fine-tuning, and inference architectures. Namely, you learned about Ray. Ray is a very good distributed framework. Distributed computing is very, very, very hard. It's not easy at all to do. And for all the reasons that we discussed, right? You have to worry about partition tolerance. You have to worry about availability. You have to worry about consistency. You have to worry about latency. Then you have to worry about routing and failures because nodes are rising up and failing all the time. Right? How do you get high availability and reliability in a world in which failure is a fact? It's happening all the time. It's a fact of life. Literally all the time, something or the other is failing. And nevertheless, you have to run operations as though there are no failures. That is the big challenge. So that is at the level of the distributed compute. But there is also efficiencies that are brought in at the level of the inference from a GPU itself. As you bring in these large language models into the fabric of inference, and you bring it into the, for example, the NVIDIA GPU or the AMD Instinct, it has to be transpiled into a language that is optimized, a data bytecode, machine instructions optimized for those GPUs. That's a pretty intricate subject. It's a pretty, the entire people who are called GPU compilers who devote all their time to thinking about this problem and bringing out efficiencies. So within that world, we learned about one of the more successful inference frameworks, VLLM. Right? I believe you did Olama and you did VLLM. VLLM is quite a bit used these days. There is some movement.
We didn't do VLLM as part of this course.
Oh, we did not do that.
We didn't do.
Then let us do one thing. Let us nevertheless release a lab so that people can do it on their own. If we can, just a basic VLLM. We do have a lab for that, isn't it, Chandra?
No, we have to create one. We don't have.
Let us create a simple lab at least to introduce people to VLLM. So what things like VLLM or SGLang and these things do is they ask this question, how can we optimize inside the GPU? So they use things like flash attention, things like that, to accelerate the inference process. And it's something remarkable. And again, I apologize. This is a very short course. I hope you all realize that we move very, very fast during this course. So there are things we covered. There are things that we didn't cover. And it's hard to, I mean, I suppose as a person who's been doing all this, to me, the subject looks vast. And at some point, we had to pick and choose what we'll cover. So many, many things. Let us say that there's far more things that we did not cover than things that we did cover. That should be apparent to you. And as you take the different courses here, many of you have been exposed to other things. Like in other courses, you might have been exposed to some of these technologies. Our hope is that if you keep taking a spectrum of courses here, you will get to know all of these tools in one context or the other. So that is one aspect of it. Another aspect of the operations side of it is monitoring and what we now call the observability of things. There again, there are excellent frameworks. We went through Comet, if you guys remember, and so forth, and the MLflow, and so forth. So we have covered a lot of things. MLflow, by the way, and Kubeflow are dominant frameworks, and Ray are dominant frameworks in the MLOps. If you don't remember anything and all you remember are the MLflow, Kubeflow, and Ray, you're already way, way ahead of the curve. So if you have assuming that you have done the labs and picked up all of this, I would say lean into it as much as you can, drill down into it and own it. In other words, make it second nature to know everything about, or as many things about it as possible. In the observability, we also today include things like, is there model drift? You can monitor for it. You can look at the logs. You can see, are the inference quality going down? So those metrics and evaluation metrics that I talked about, you can use it not just before deployment, but in production. You could be sampling the responses and checking to what extent, every once in a while injecting it with your test set or goal set and seeing, is your model doing well and how well are the quality of the responses. And sometimes it needs human feedback. A large part of it is, especially in the world of LLMs, there is a lot of human feedback and alignment problems you have to solve. In other words, mathematically a response may be good, but does it align with human expectation? So for example, if you were to ask this question, what's the capital of, let's say, France? Does it say Paris, or does it instead ask you, what's the capital of Germany? Now, from a mathematical perspective, both answers are equally good, because one would venture to say that on the internet, there are as many list of quiz questions like this: capital of France, capital of Germany, capital of this and that, and with no answers, as there are statements which have what's the capital of France? And then here's the answer, it is Paris, etc. So the machine can, with reasonable probability, maybe lean more on one direction than the other, but nevertheless, it can quite often fluctuate between the two. Whereas the human alignment would say that no, you need to answer the question, not reciprocate a question with another question. That is the question of alignment. Does it align with human expectations at all? And when it comes to alignment, it also brings up other ethical issues, alignment with human values, right? For example, does your machine respond to a question about how to make a bomb, which it shouldn't, right? And does it, or any destructive questions? I mean, these are destructive thoughts it is an unfortunate fact, but these are part of the human condition. Whether we like it or not, it is a fact that questions like this, how to make a bomb, how to kill my spouse, how to kill my boss, are rampant. They are far more common. And as Google searches, analysis of Google searches have shown, or many searches have shown, than one would like to admit. And those people have obviously, over the years, trained their systems to deal with those questions very, very carefully. And a very similar thing has to be applied to machine learning models. It would be terribly dangerous, or it would be a catastrophe if the LLM very helpfully gave you a recipe for that, and then the user went out and acted upon it. Right? So that is it. Or there are examples in which people ask, how do I kill myself? Right? What's the easiest way to die, and things like that. And you do want to be careful how your machine is responding to those questions. There was a meme that went around many years ago, which was, I think, from an Indian instance of Amazon, or was it from another e-commerce site, in which somebody was purchasing a ceiling fan, and the recommendation system very helpfully recommended a rope and a stool to go with it. Now, that is not something that you want to encourage people to buy every time they buy a fan. So that speaks to human alignment and safeguards. You need to worry about safeguards around, especially the large language models. Now, obviously, we couldn't do it in this course because of again, the shortness of this course. But one of the things that I would strongly encourage you to do is look into guardrails around large language models. And there's a significant effort to build out guardrails. Those efforts are, let us just say, in a very early stage. Almost all of the guardrails can be easily penetrated today, which is an unfortunate fact. But with time, hopefully, we will have a better handle on how to prevent problems with these AI systems. There's a tremendous amount of research that is going on. Two open source projects that are quite admirable in this space are, one is literally called guardrails.ai, and the other is the Llama Guard. I very much encourage you folks to look into these two open source projects. Okay? So now in this course, and I will talk about the scaling laws as a new topic today, but more than that, let us just review what we did. We learned about Jenkins as a general purpose execution or workflow management framework, like pipeline management framework. We did Kubeflow and Airflow. Airflow is again a general purpose pipeline management framework or workflow management framework, orchestration framework. Kubeflow, on the other hand, is much more AI specific, machine learning specific. It is based on the Kubernetes. It's very cluster aware and based on the Kubernetes framework, which is rock solid. Like Google, I think the statement Google makes is that we run planet size clusters using Kubernetes and it works reliably. So obviously Kubeflow is as a cluster aware or cluster a Kubernetes based pipeline management. Amazing. And it has a very, very good support for many aspects of AI workflow or MLOps. Um, uh, I mean, I can think of quite literally as I'm thinking, and from the knowledge I have of what many commercial companies do in-house, I can tell you that there are countless deployments of Kubeflow internally as the production MLOps. So, but Kubeflow's demerit is that it's complex. It's a little old API. It's complex. It takes a long time. It has a pretty stiff learning curve. So we tried to make it a little better for you by giving you a head start into it, like easing your way into Kubeflow. Now, please continue that. It's a big thing to do. Do that. Then MLflow is a little bit gentler and easier to deal with, and yet a very mature framework. It also has observability and data management, model management, and these things built into it, which are very nice things. We talked about it, MLflow. Then we did observability with weights and biases and comment and so on and so forth. And then we got into Ray framework. We did Ray core. We understood the foundational ideas of distributed compute. Then we did various labs in Ray, putting models into Ray, training the models, and then using inferences with those models and so forth. We did computer vision models and so on and so forth. So that has been the course. That is where we are. How much of MLOps have we really covered? Well, we have covered all the broad areas of MLOps. If you know this much, and if you really have practiced this much, you're way ahead of the curve. But while that is true, nevertheless, we have just seen the tip of the iceberg. It's a vast field, and it is a field that is fast exploding. There is no amount of learning you can do and feel that you have wrapped your entire arms around this field. Right? Because new topics in it are springing every single day. Like, for example, LLM as judge, as I mentioned to you, it's a very recent phenomenon. Prompt management is within the year. Prompt optimization and prompt ops operations and prompt metrics and so on and so forth. So things are moving very, very rapidly. And as the laws evolve, like, for example, I would not have initially, one of the reasons I didn't bring it, the ethical or the bias aspect into the labs of this course is I had to pick and choose the topics. And when we started this course, made a decision that we could leave it out. But today, I'm not so sure anymore because search for bias and adverse impact are quantifying that, or at least showing due diligence that you did enough to verify that it doesn't happen. Now, the governments are in different geographies, making it the mandatory aspect of MLOps. So that I would leave as a topic for you folks to continue and follow through and learn on your own. So what I will do today is, today being the last session, usually it is a wrap-up session in which we cover everything. And we leave the last hour for question answers and just a general discussion on the value, taking your feedback, what we can do to make this course better and so forth. What I would like to do is talk a little bit about the model optimization aspect. How do you, the neural scaling laws that I promised we'll talk about. Let me do that. Well, I will. Change the page color because darker seems to work better. Let me know if you guys can see my screen.
Yes.
Okay, so here's a fact. You have a large language model, let's say LLM, a transformer. And this is, I'll sort of take a slight historical perspective on this. The way this started, and it seems like ancient history, what we are just talking about 2-3 years ago. When you have a large, like what we today call a large language model, but let me just call transformer. What people began to do, and there was a paper in, I believe it was 2020, at which time there was models like GPT-2, not terribly capable, but still quite remarkably good for their times and showing promise. People began to see very interesting and promising qualities to those models, those like GPT-2, etc. What they observed is that bigger models are more powerful, more capable in some sense. And they hypothesized, they began to research, is this really true? And then there was a discovery of the neural scaling laws, which seems to apply broadly to all neural architectures, right? So what the neural scaling laws say is this, and I'll sort of simplify it down because I don't want to go into formulae. Imagine that you have 3 dials that you can play with. Data, right? More data. The other that you can play with is more parameters, bigger model. And the third dial that you could play with is more compute. So what people realized is that you could, for example, let's look at the compute. What happens in a compute is if you keep your data fixed and your model parameter, you have fixed your model, then all of us know that if you're looking at the performance of the model, let's make this the performance parameter, performance, then and this is compute. A simple way to think of compute is number of iterations or steps of training the model, how many batches you ran it over or epochs you ran it over, pick your thing. Then you would see a behavior like this. Eventually, you would realize that your performance asymptotes, your loss function, let me just put it this way, your loss function, eval loss, would asymptote. This is something we are all familiar with, isn't it? Now, what happens if you make your parameter bigger? You bring in more parameter. And what people began to notice is that, suppose in a small model, you, let's say, asymptoted here, with a bigger model, you will asymptote a little bit lower. With an even bigger model, you will asymptote a little bit lower. Does it make sense, guys? Right. And there is more to it on a log scale, actually. And now, so this is what it speaks to is that bigger models are better, right? Better performing. Along the way, they also noticed that better has an interesting meaning. They might have been really bad at doing arithmetic, but after a little while, they begin to do acceptably well at arithmetic. Right? And people began to speak of the so-called emergent phenomena in this context. Then they also noticed that, see, making your models bigger without increasing your data size would be catastrophic. Why would it be catastrophic? Because these models tend to, when you train a model, it is the nature of neural networks that big models, they preferentially first memorize the data. They overfit the data, right? And very much like human beings, right? If, for example, you knew that a professor year after year asks one in the exam, there is a bank of questions, let's say 100 questions. And what will come in the exam is recycled, a subset of those questions. And from university experience, many of you would confess that students are very good at building up these question banks and passing it down the generation. What it leads to is a sort of subversion of the institution of learning, because in those particular courses, most students find it foolish to go actually study the subject and learn it. They would rather focus on other subjects, and in this subject, they just memorize the answers to those questions. And they get by. They get A grades and all of that, if that was true. And obviously, it's because the data set that is used to test them is well known and small. A similar problem happens with neural networks. You take a large model and you train it with finite data, let's say data size D0. What happens is that it will try its best first to just go memorize the data. And unless you train it with more data is a regularizer. The simplest regularization technique you can apply to a neural architecture after you have done your L2 and other regularizations and your dropouts and so forth. You can try all of that, but if you don't bring enough data, machine will memorize it. Now, the easiest cure to that problem is to go with another data set, which is bigger, D2, and so forth. And as you make your data set bigger, training data set, training data set, then the performance on an eval data set goes up. Then the performance on the performance keeps going up, right? So more data leads to, so you have a similar graph, more data, the same size model, more data leads to lower loss, eval loss, right? Or test loss on the test data set. And so more data is a regularizer. It's a known thing. It makes model better. But there is now a problem. See, you cannot just, suppose you take a small data, a small model, and you go on increasing the compute, it doesn't quite help. Think about it this way. One easy intuition and that one could apply is that if you're trying to build a straight line approximation to data, right? And let us say that your data is something, let me take a shape of the data. Suppose your data is like this. And your machine infers that this is the model. And there is another data which is like this. And if you use a very small model, in this particular case, linear regression model, then you would agree that your machine, the best that your machine will do is build a model like this. You can convince yourself that beyond a certain point, you will reach an asymptotic limit. There is no better straight line that you can fit to this data, isn't it? So bringing more data becomes fruitless beyond a certain point, right? The loss function is not going to get better. Bringing more compute itself will not going to get you better. The machine will basically say, I've figured it out. This is it. You want a straight line? Here's a straight line. That is, of course, a vast oversimplification on what happens in a neural network, but not far off from the intuition perspective. If you take a small neural network and you train it with more and more and more data, and you make throw all the computes and all the data that you want, nevertheless, the loss would have asymptoted, right? So what it means is that if you need to scale up your model. As you scale up a model, for every model, there is the right amount of compute to reach asymptote, loss asymptote, and there is a right amount of data that is needed to reach that. So that was the discovery of the neural scaling law. That is what the neural scaling law says, that you need to scale up the data, the model parameters and the computes in a coordinated manner. You have to bring it up. And as you bring it up, your model gets better and better. Now, while this theory is correct broadly, this had actually far-reaching implications. If you go back and look at the history of our field, GPT-1 and GPT-2 were still things that you and I could download and run. But when the neural scaling laws emerged, people made a big bet, in particular, OpenAI made a big bet. They said that if the neural scaling law is correct, then what it means is we just need to go grab a lot of hardware, we need to go grab a lot of data, and we need to scale up the model. Because a much bigger model trained on far more data and far more compute is likely to have far better performance than GPT-2. And that is how they bet on it. And they created GPT-3. When they created GPT-3, it sort of validated their belief in the neural scaling laws. And then, of course, the rest is history. GPT-3 was followed with GPT 3.5. In GPT 3.5, the other big idea that came, of course, is instruct GPT. How do you do? Pre-train a model, follow it up with supervised fine-tuning, follow it up with reinforcement, human feedback, RLHF, reinforcement learning on human feedback. And at the end of it, what came out, as you know, as is history, using the 3.5, was the basically the emergence of the chatbots. It led to ChatGPT, right? Which more or less changed the world. Transformers used to be the plaything of engineers and researchers, perhaps 10,000 of them around the world. Overnight, they became a sensation that a significant proportion of humanity was engaged with. Right? It had almost the most astonishing growth or adoption of a technology has been that of these LLMs or these chatbots. This has shocked everything. Any other thing before that, whether it's the social media or anything else, took far longer to get adopted, but this really got adopted. And it speaks, it's a testament to the validity of the neural scaling laws. Along with that are two ancillary facts. One of them, right after that, people began to observe that as you make this model really, really big, you start noticing emergent abilities, things that it couldn't do. Like, for example, you notice that these machines are forming concepts internally. For example, there's a concept of psychopansia, flattery. There's a concept of the Golden Gate and concepts. They reason in concepts. Another discovery was that these things actually do, if you ask them modular arithmetic, for example, they actually learn modular arithmetic by drawing a clock in a latent space representation. And in the clock, they just, like, for example, how do we do? Clocks are the classic example of modular arithmetic in the case of clock by 12, right? So 5 hours from 10 o'clock is 3 o'clock. How do we do that? Just move past in the circle of a clock, 5 steps, 5 hours, and you'll end up at 3 hours, right? 3. So, and most people don't figure out that all modular. I mean, you can ask this question amongst your friends and see how many of them, if you ask them to do modulo 97, for example, they will immediately draw a clock of 97 in their mind, right? So that speaks to the fact that these machines are doing that internally is an amazing testament to the emergent abilities and to the neural scaling laws that are happening with these and these concepts that are getting formed. The other great discovery that came somewhere along the line and took, and then, by the way, people found that these machines have a theory of the mind. They actually, before they respond, they look at your question and they figure out what is it that you are thinking? What is it that you could be thinking? And theory of the mind was supposed to be a privilege of only the human Homo sapiens. We were stingy enough not to even ascribe it to our very, very friendly dogs or to our neighborly apes, the chimpanzees and the gorillas, the great apes. We insisted that only humans have a theory of the mind. Only humans know when they're communicating with another person, another instance of their species, what the other person may be thinking, and modulate what they say based on what they think the other person is thinking. But it turns out now there's fairly strong evidence that these machines have a theory of the mind. Right? There are discoveries that are coming out that are so astonishing as these models scale up. And it keeps reminding me of the old physicist paper, more is different. I believe this was 1970 or 71, somewhere around the time. Look up this paper, More is Different. Profound paper. What it basically says that you may be wiring bigger things with just the same little primitive thing, like the neurons. And you may think you know all about neurons. So obviously there's more. More is just going to scale up performance or do better accuracy, but actually more is different. When you boil a little bit of water in your kitchen, in the kettle, it leads to steam. That steam goes away. But if you boil the ocean, you get clouds which have that have thunderstorms and hurricanes, and that rain down, and you have dew, and you have snow. And it's not so easy to immediately foresee that instead of boiling water in an ocean, if 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 as the sun does, it boils the ocean itself, boiling the water in a kettle instead. You move from there, scale up to the sun boiling the ocean, which is what takes place. Not boiling, but evaporating the water from the ocean. It would lead to such beautiful and wonderful phenomenon as snowfall and snow formation in the high altitudes, and to hurricanes, to clouds, beautiful clouds and wonderful sunsets, and to rainbows, right? That it would lead to rainbows. And but when those things happen, physicists immediately are able to post hoc explain it in terms of the theories of physics. A very similar thing is happening with AI and with these machines. As we scale up these machines, they often take us by surprise. And then post hoc, we think through it, we reason, and then we say, aha, we got it. Now we understand why it happens. But the surprising thing is most of us couldn't have anticipated that we would see those things. Right? So that is the neural scaling law and the emergent phenomenon associated with it. Emergent phenomenon associated with it. There's finally a last thing that I didn't talk about. It is grokking. Grokking is yet another mysterious thing, and it is something that actually is a decision point for MLOps. Suppose you have only this much data. You have this giant model, big model, and you notice that your loss function has plateaued, right? Your number of iterations. And these are real problems that MLOps engineers have to make. Do you have to inform the team that your model is trained and it's time to stop? Or should you not do that? What would be your response? Anyone? Like I said, that ultimately the loss plateaus, the eval loss plateaus after some time, right? After a certain amount of compute. So isn't it a sensible thing to say, all right, once I see a plateau, once I see an asymptote in the loss over time, loss over compute, it's time to stop the machines and free up the resources to give it to another team that has been waiting in the wings. Wouldn't you do that? Wouldn't you clear up the runway for the next plane to take off? Any questions? Anybody would like to hazard a guess? Look at this, guys. I don't know if you're paying attention, but would you not say that it would be time to stop the machines? Because that's
What about the training loss? Is it also
training
plateaued
loss.
out?
Training loss will forever keep going down. That is, remember, a red herring. You never look at the training loss. Training loss always keeps getting lower and lower and lower. And so you don't even consider it. I don't even consider it in these graphs. You're just looking at the eval loss, and your eval loss has asymptoted. What would you do? Time to stop the machine, isn't it? Isn't it a common sense answer?
Yes, sir.
Yes, it's a common sense answer. And yet came a most remarkable discovery that put common sense on its head. What people found that one of the most mysterious things with neural architectures is that, most surprisingly, if you continue doing this, it goes on and on and on. And suppose you let the machine run, it suddenly goes through a grokking movement. And this happens. Namely, the machine the loss of the machine, eval loss, has an unexpected and a precipitous decline in the loss. You end up with a far better model. Remember, you still have the same data, fairly small size data, let's say. Right? And yet, if you just let the compute run on and on and on and on, what will happen is this machine will go through this is what physicists call a phase transition. So an analogy of this is you take water, which may be at, let's say, room temperature. You keep heating it up. What happens on a kettle? The water looks like water, isn't it? It might bubble up a little bit, but it more or less looks like water. Would you agree? Especially if you slowly heat it up. But then when it reaches 100 degrees centigrade, there is what we call a phase transition. It's sort of, there's a phase change. Once it has gotten the latent heat, then it transitions at 100 degrees. And at 101 degrees, it is steam. It has gone from a liquid to a gaseous state. Likewise, if you take water, and so the volume precipitously expands, right? The same volume of water leads to a far larger volume of steam. Or if you were looking at the density of that, so for example, think about it this way. As time passes, as temperature increases, if you were looking at the density of the water, what will happen? The density of the water will go through a plateau, more or less, slightly decreasing, maybe slightly decreasing. And then it will precipitously go through a phase transition, isn't it? Because steam is far less dense than water is. And do you see a similarity between these two graphs? That's why it's called a phase transition. Grokking, this thing has a name called grokking because something very deep and profound happens inside the machine. What the machine starts doing is, in the beginning, it has memorized. The moment you give it small data, not enough data for this big machine, big model, it will say, oh, easy, I'll memorize it. And it holds on to its memorization because it's seeing the same samples over and over again. However, it is making little adjustments internally. And believe it or not, and we don't quite understand the dynamics of it, but what it is doing is, even though it's holding on to that loss, we believe, and there are many hypotheses, but my hypothesis, which is probably wrong, but for what it is worth, is that in higher dimensions, there's lost landscapes. They form ravines. So even though it looks that the loss has plateaued, the machine is exploring different points in the ravine of the lost landscape. And then it somehow comes and realizes that, this particular ravine is actually at the top of a mountain, of a hilly region, of a plateau, and that there is a deeper ravine, there's a deeper place to fall down to. In more practical terms or language, what happens is this thing that has memorized suddenly learns or groks what really the data is trying to tell. What is the generalization of the data, the generalized model of the data? And when it groks, now it doesn't need to memorize anymore. So in this region, it is actually actively trying to forget memorization. It actually forgets the memorization and then stays with the generalization. And that is it. That is the grokking moment that it encounters. So the question for you in MLOps is, again, a hard to answer question. You are sitting here. At this moment, should you tell the team, it's time to end now, you're done. Your machine has asymptoted, has done the learning, and we are freeing it up. We are taking a checkpoint of the model and freeing up the resource for another team. Or do you let it run on and on? And these are practical decisions. These are economic decisions based on the amount of resources available in your company and how severe the problem is. For example, if it is a mission critical problem, if the destiny of your rocket depends upon it, let's say, on this model, and then of course you would say, let it run on for a few more days and let's see if grokking happens, or it may or may not happen. If the data was sufficiently large and the machine has already generalized, then there would be no grokking bonus at the end of it. Right? On the other hand, if the problem is not that critical and your checkpoint is already saying, hey, for practical purposes, this model is useful, maybe it's time to free up the resources for another model to get trained. These are real practical considerations for MLOps. The other practical consideration in the same landscape is somewhat not in the hands of MLOps per se, only sometimes, but I'll just mention it because it does come up, which is that of the double dip. We are all told that as you complexify a model, you will go through this sort of the eval laws, complexity of the model. Right? So imagine that you're doing polynomial regression and so forth. So in other words, what happens is that in the beginning, most of the loss or eval loss comes from the model being too biased, too stringent, too opinionated, or have you picked. It's not flexible enough. So it can't learn much. Then after a little while, what happens is that it reaches an optimum here, which is why people call it the bias variance trade-off, because then loss again starts increasing because this is the variance loss territory. This is where variance loss dominates. And before this is the bias loss dominant territory. Right? And so every single machine learning, classic machine learning textbook, in very early, they will mention this classic figure of the bias variance trade-off, which is fine. And you don't want to have a very complex model. The trouble with neural networks is, for reasons we don't understand, there comes a time where something very remarkable happens. Complex models actually, counterintuitively, after reaching a certain level of complexity, you make the model more complex, bigger model. They learn to actually generalize better and get rid of their overfitting. And do you see there's a resonance between this, some sort of a causal, maybe people have speculated that grokking and double dip may be related somehow. But what this machine seems to be doing is it internally simplifies itself. It is as though it finds the optimal simple model or internal sub-circuit that represents the best generalization of the data. So this is the double dip issue. And the way to MLOps it would present is, suppose you know that beyond this point, let me say model optimal, M0, optimal model, you make it any bigger, people are noticing that the model gets worse. Do you insist on that and say, don't waste our time, don't waste our resources, stick to M0? Or do you let that engineering team or the scientific team come and bring bigger models to you? It's a hard decision. There are no answers because will the double dip take place? You don't know, right? But generally, there is double dip observed in large neural architectures. So there is a lot of mystery actually that makes MLOps and LLMOps in particular extraordinarily more sort of experience and bit of a black magic, sort of a experience and magic driven rather than just rules of thumbs driven. See, if you think of many of you have been doing DevOps or ops, just system ops, and system ops are predictable rules of thumb. At the end of the day, you know what will happen if you let a machine, a server, run at 90% utilization? It is likely to fail. It is under excessive load, right? So you try to run it in well-conditioned manner, definitely below 70%, but more like, if you can afford to, at 50% CPU and memory utilization. By the way, Jay, is that still the norm in large enterprises? Hover around 50% for mainstream jobs?
The resource target, right?
Yeah.
Yeah, I mean, it's 50, 60, that's ideal, yeah, goal. Yes.
Ideal utilization problem. That's right. So we do know, system ops, MLOps, etc. Things are predictable. We know things. We run Terraform scripts. We know what we'll get at the end of it, the setup will end up with, and things like that. MLOps is not that straightforward. Many things, there are too many moving parts. Unlike just software that you deploy, training data is evolving over time. It has a temporal nature to it. Models are tied to the data they're trained with. Models are also contingent. They have come with a vast number of hyperparameters. Now, in this course, we did manage to teach you about hyperparameter optimization with MLflow. There are too many knobs that you have to figure out what's the best value. And it's a very thorny problem. How do you figure that out? How much resources do you devote to figuring that out? Then models have this whole problem that, do you scale them up or not, given the data? Do you allow more complex models to be built, given that you know what the size of the data is? And engineering teams, research teams will always knock on your doors and say, have you gotten bigger data yet? Have you cleaned up the data, right? Because one of the lessons is you can basically get more quality or better models with cleaner data, higher quality data. So they will clamor for data quality. If you are in the MLOps, you will realize that you will be you'll have a target painted on your back, because just about everybody will tell you that their models are not good because the data is not good. Data is not good because MLOps is smoking pot. So it's a thing to wonder, where do you spend your time? You have only finite amount of resources and time to work, and where do you spread? And to make matters worse, how long do you let the compute go on, right? Because what if there's a possibility of grokking? And so you need to learn about all this neural scaling laws, about grokking, about double dips. You have to be very sensitive to that. You have to be very sensitive to what data brings. And then finally, if that was not enough, in the world of MLOps, there is one more consideration, which is a runtime consideration. To the extent that large language models are stochastic parrots, right, in their responses, and they're stochastic, they're not deterministic machines. When you take a model, you have two axes to worry about. To get better responses, your business team, your product managers would say, hey, let's use the biggest model we can. And they would say, okay, let's go to the frontier models. Let's go to Anthropic, OpenAI, Gemini, and use the biggest model that they offer. Problem is, there is a token count price. And there's an exorbitant price that you will be paying. Then questions that come up is, can you get equivalent performance from smaller in-house models? Why would you do that? In-house models preserves the privacy and confidentiality of your internal data. The data is not getting shipped out to these frontier models. It's not leaving the extranet. So what people do, there's a host of techniques people have come up with to get better inferences from smaller models. And at inference time, you can use not just one-shot inference and give the answer, but you could do all sorts of things like ensemble of inferences, ensemble of answers, and take the majority, very much like random forest takes the majority vote. In the same way, you can do a vote on the answer. You could do you could do many things. You could couple it up with a verifier. You could couple it. In fact, that's one of the papers that the large language monkeys that we covered previous Wednesday. So at inference time itself, there are many things you could do. You could use an ensemble of small models and take a majority vote onto that. And that all is, again, the moment you say that, in principle, it looks as an idea, it looks elegant and beautiful, but it's a headache for you as MLOps, because you have to go and productionize it, wrap all of it around observability, track it, see whether it is really superior, right, in production. And what is the cost in terms of hardware resources, budget, time, latency, of all of this complexity that you bring in to all of that. So now inference itself is becoming an area that is actively being explored with innovative ideas. There was a time when you would say, okay, model is trained, I give it an input, and here's an output. And for better or for worse, that's the output. But we now live in the world of LLMs, large language models, in which, to the extent that they are stochastic parrots, once the answer may not be good, second time the answer may be brilliant. And then you need something to shift through the answers and sample through the answers and pick the best one. Gets yet another game going. Then recently, and that's going to have a huge impact on the MLOps, especially LLMOps, is the emergence of the agentic reasoning, AI agents. The future belongs to AI agents. If I were to make one prediction and say, just like from machine learning, like from neural networks, the discovery of the transformer, when LLMs came, or these generative models came, the whole field of generative AI became an explosion. And we have been in that explosion now for the last 2 years, 1.5, 2 years. Right? It would be perhaps not too foolhardy to prognosticate that in the coming year or so, and from hereafter, the big explosion that will emerge out of generative AI would be agents, AI agents. And you can see that some of you, I think, any one of you here who is part of the AI agents class, anyone in this class was part of the agents?
Albert is.
I'm here. I think Sanjeev also is here.
Sanjeev is also okay. And as you would agree, AI agents, they are inference time engines, right? You take a task, you take an input, do a very careful decomposition, you do planning, you do collaboration between various so-called agents, each of them basically an LLM, or at least temporary transient LLM, wearing a hat, wearing a role and a goal, going about their business, collaborating, using tools, calling functions, calling code interpreters, calling open functions on the internet, searching the web, doing things. And all of this complexity of the agentic world or multi-agent systems, the word people often use is multi-agent system. Or more simply, what I call collaborative team. Now it has become a team activity between agents. And this multi-agent systems, and at this moment, take it as a fact from me, they are so compellingly superior at a large number of tasks compared to just using a single LLM, that we are beyond the point of debate. There's fairly strong consensus in the field that the future belongs to multi-agent system and multi-agent reasoning approach to almost all complex problems. What does that do? Go ahead.
Asif, what do you think about this N8N framework, the workflow framework?
It's a function framework. See, if you look at Zapier and N8N and all of these, they are people who are integrators, right? They make all the APIs, commercial APIs, available to you as tools for agents. So they do have significant value. See, the core concept of an agent is it's like human being. What do? We have our 5 sense organs. through which we sense the world. We see, we hear, right? We touch, we smell, and so forth. We sense the world. So agents have, likewise, they have sensors and they have actuators. This is the classic theory of agents. Any actuators, actuators, and there's no I there, of course. Actuators, sensors and actuators. But today, when we use LLMs, if we use LLM agents, AI agents, LLM agents, we just wrap it up by saying both the input and the output we do through tools. So what is the job of a LLM agent? A simplified version of an LLM AI agent is, and I'll just use the word AI agent because it's true, whether it's a LLM agent or not. It is a bidirectional interaction with the environment. And that's what an agent is doing. And in a multi-agent system, it becomes AI agents who are internally, of course, interacting with each other. Right? So they are interacting with the environment and they are interacting with each other. So now what happens is these things are the tools. Now, search is a tool that will help you search the web. Right? RAG is a tool. So for example, you can have a Google search team, Google search, or let me not use the word Google because it could be a big or something. Web search is a tool. Your document search itself is a tool. Like, for example, your semantic search into documents, into your PDFs is a tool, right? Your compiler, your interpreter and compiler. For example, if you have a Python interpreter, it's a tool. You can write some code and verify whether it works or not, right? Your Unix shell, bash shell, if the machine has access to it, is also a tool. In the same way, open functions of Gorilla, for example, which looks at PyTorch, Hugging Face, etc. They are tools. Those API, open function API, gives you a tooling to write code against all those systems. So in that same framework, people, the moment open functions came out and these things became real, people realized that what you could do is there are these companies, Zapier, etc. Their entire core value proposition is they give you seamless integration to thousands of tools. You want your Slack to be integrated with your Google Docs. The easiest way that you can do it is using all of this Anit and Zapier, etc., etc. Anit, and I don't personally have experience with, but I'm told is very good. Right? So these are tools, API integration tools. Any software that has an exposed API, these companies or these frameworks, they give you API integration tools. That fits in very neatly as a complementary. It just empowers the agents, isn't it, Albert? Because agents, the more tools you throw at an agent, the more empowering it is. Right? The larger the repository or arsenal of tools you make accessible to your AI agents, and then you give it a task, the more likely it is that the agents will be able to solve that problem with the available arsenal of tools. Yeah? And that's the value of these things.
We have a very nice UI to just put in blocks of agents and then write your prompts and everything. Like a UI, just like similar to AutoGen has it.
Yeah. See, I think they do that. I mean, agentic reasoning. See, here's the thing. If you look at, and again, this now goes into subjective, and quite likely I'm wrong. So let me put that caveat. But if you look at the Zapier and all of these, these are great API integrators, and they have lovely UIs to integrate this with that, and I think they're amazing, right? I wish all of it was open source, but it isn't. But it's still amazing. And now, if you look at them, isn't it logical for them to ask, okay, as the agents, AI agent theory develops, LLM agents develop, they are in prime position to leverage that. All they have to do is integrate the agentic reasoning into their frameworks because they already have API integration tools, isn't it? They have a vast arsenal of tools. And so it makes sense that they will augment themselves with agentic reasoning. Everybody would. I mean, I have been to recent conferences in AI. Just about like there was an HR conference. I wasn't physically there, but I was indirectly there. Just about every company out there in HR space, they were singing songs about agents and agent integration into their software. Right? Quite literally, it seems to be the topic. You know how it is in Silicon Valley and with software companies. The marketing team will go ahead and sing songs about a technology which the engineers are still just beginning to implement. The easiest way to know what is the future is simply to see at these conferences, what are the companies talking about? Because whatever it is that they're claiming they have, you can be almost certain they don't have it. They aspire to have it, but it gives you some window into what they aspire to have in the future. And therefore, some part of it will come real. So anyway, guys, it's been a long course, a long session, and I won't continue. It's almost 9 o'clock. I want to leave some time for this. By the way, this session, I saw a message. This session will stop in 2 minutes. Is that really true? I thought who
No,
created?
recording will stop in 2 minutes. That's Jorge is saying.
Why is that? I don't. Why should that happen?
Yeah, actually he has to explain. Jorge, what's the reason behind it? Will you mind writing it down,
Yeah.
replying it?
No, we may have gotten some message accordingly that it might stop. So, all right. So, but he has a good advice. If it stops, we can get back in, and we will get back in and restart it. All right. So, guys, what I would suggest is if you go to the course portal, and I suggest you do, you will find a wealth of resources here. Like obviously all your code is here. It will be here for all perpetuity, right, till my machine dies or support vector shuts down, but which hopefully neither of them should happen. But it is there. But there are also other external web resources which are lovely. They're just lovely. So these web resources, I would strongly advise you to engage with. Awesome LLMOPs, a curated list of the best LLMOP tools for developers. Let's go look at it. If you have not looked at it, now is finally the time. Let's go look at it. And you will notice that, look at it has close to 4,000 stars. And just this list, this information has been forked 362 times. Right? 69 people have helped curate this list. What do you see? There are so many things you can do for any one of these, right? Models, model serving, large model serving, frameworks, servers, observability, we talked about, vector search, etc., etc. So it's a huge wealth of information. And each one of them has, like, it then goes into considerable detail. How do you serve a model? Well, we talked about, we will, I think you'll get some exposure to VLLM. You have seen model serving through Ray framework. Right? But there are other frameworks. In fact, this thing needs to be updated. It doesn't mention SGLang, which is emerging fast. Oh, framework serving for serving. Okay, it must be here somewhere here. Triton, Ray LLM. So Ray LLM is what you guys got exposed to. But there are more coming. There are more coming on a very, very regular basis. So I would strongly suggest that you become, or at least browse through these frameworks. I myself learn, like one reason I keep track of these systems is you come to these and every time you come to this curated list, you discover something that you didn't know about. And then you have to make a decision whether to go down that rabbit hole or not. And it helps to have a community. And support vectors, we do have a vibrant community. Reach out on Discord, talk it about. Somebody or the other in the community would have played with that resource and would have an opinion about it. And it can sort of shape your decision to go down that rabbit hole. Because you can't go down every rabbit hole, right? So that is something worth doing. Then going back to it again. Awesome LLM, yet another curated awesome list, right? About the LLMs that are there, right? And you see this, I love this visualization actually. It's been, you literally see how the bigger models have been growing in size. And so here is the scaling law for neural networks. It's a good review. I hope that you will study it. So look at the date, 23rd January 2020. See this paper, at the end of it, OpenAI and Google and others, they bet big after discovering the new scaling rules. There's also something quite mysterious, actually. I didn't cover because it doesn't pertain to MLOps, but I'll end by saying there's a bit of mystery. Do you see this line? By the way, this is on a log scale. But having said that, did you see this, what it looks like a diagonal line? For some reason that we don't quite understand, it seems to represent some inherent frontier to how well these language models can learn, despite their sizes and despite the data and despite the compute. None of them seem to be crossing that frontier of performance. We don't know why. Another mystery that we face with these language models. Anyway, so that's all I have, folks. My request is, do stay engaged. Do please review the labs, finish the labs. We'll try to put a little example on VLLM. Also, there will be a lab, a final lab, but for theory, this is the last session. Nevertheless, it's not the last session for the course. There will be a lab session. And after that, it does not end there. Periodically, we'll be releasing some little bits if we do some prototype or some POC or something that we feel you folks will benefit from. So we'll put a message onto the Discord saying, hey, here is something new. Why don't you take a look? It might benefit you. So we'll continue to do that. And with that, I'd like